floating water bridge. Before I start, the last speaker had a very, very interesting presentation, and I'd really like to hear more about that new gravimetric model, because my friend Didattica, who is here in the audience, and we were traveling to solar eclipses over the past 4 years, measuring water properties, and we found interesting stuff. But so far, we don't have any explanation. And this presentation is about something completely different. But nevertheless, I just wanted to mention that I would like to talk about models, for example, also models by Klaus Volkhammer, who is also here in the audience, that could actually explain these effects. But let me now, first of all, thank the organizers for inviting me. Thank you, Jerry, that after so many years, you still want to hear something about the water bridge. Thank you very much. And of course, thank the organizers of this conference for giving me the opportunity to talk to you about the floating water bridge. Now, in general, for those of us who have never heard me speak before, what I do is I work with high voltage and water. And I'm sure everybody of you has at some point in your life heard that you shouldn't do that. It's extremely dangerous. If you pour water on machinery that works with high voltage, it breaks. If you use high voltage while you're yourself immersed in water, for example, you're in the bathtub and somebody throws a hairdryer into that tub, you most probably will die. So please don't do that. Now you might ask the question, if it's so dangerous and destructive, why do it at all? Well, and in that case, I'd like to quote the Austrian forester Victor Schauberger, who said, "Let us understand and copy nature." Now you will ask, why nature? What does high voltage and water have to do with nature? Well, I say it's a matter of perspective. If we take a look at our beautiful planet from the International Space Station, we see that the interaction of high voltage and water takes place very frequently and has been taking place for millennia on this planet. And I think if nature does something, it has a reason for it, and it's worthwhile studying that phenomenon. Whereas the dielectric breakdown, so the lightning, is worthwhile studying, before we study lightning, at least this is what I thought, let's look at what are the precursors for lightning. How does water, before there's a breakdown, react to strong electric fields? And one of the phenomena that we encountered when doing this research, and what this presentation is about, is the so-called electrohydrodynamic liquid bridge, better known as the floating water bridge. This phenomenon was discovered in 1893 by Sir William George Armstrong. He took 2 wine glasses, filled them with chemically pure water, then he submerged 2 electrodes into these glasses. Back then he also had a cotton thread connecting the 2 glasses. And when he applied a voltage from a Van de Graaff generator, which was back then hand-driven, to his astonishment, there was a watery connection between these 2 beakers that would even be stable if you pulled the beakers apart. Now, if you look at this in real time, it looks something like this. You have your 2 beakers here. You have the electrodes submerged, and as soon as you apply the voltage, the water jumps up and forms a macroscopic connection. And you can see that very quickly the levels in the beakers change, which means that there is water flowing through this bridge, suggesting it is liquid. On the other hand, if it's short, it looks like a stiff cylinder, suggesting it is solid. If you continue pulling the beakers apart, you will see that it's hanging like a catenary. So this is different from what a liquid would do, and it's also different from what a solid stick of ice would do. So it's probably, even with the naked eye, you can see that this is something in between the liquid and the solid. And I have told you over the past years many very complicated things about the bridge, investigations, quasi-elastic Newton scattering, ultrafast, infrared relaxation. Anyhow, there is another very simple optical method which I would like to show you today. And this method is called shadowgraphy. It's very, very simple. You have a camera, a light source, a beam splitter, a retroreflector. This is the kind of material that traffic signs are made of. So it has a certain grain size, 0.5 millimeters, and any object bigger than that size will be reflected onto itself. So the bridge, which is also here, of course, as you can see in the middle, which acts as a lens, will first focus the light onto a spot about 1 centimeter away, and then it will be spread out onto the retroreflector, and from that it will be focused back into the bridge and then into the camera. Well, what's interesting about this method, it can visualize small changes in reflective index of objects smaller than his grain size, 0.5 millimeter, whereas bigger objects just look like normal visualization. So to show you this as an example, if you put the spouts of the two beakers together, you start the bridge, and this is how it looks like. The water crawls up, and you have a highly transparent cylinder of water, and with the naked eye you don't see anything. It's just transparent. If you take shadowgraphy, you see that the contrasts are much stronger, and if you start the bridge, this is just a normal camera, it looks different. It seems as if it's dirty. There seems to be something inside of the bridge, and whatever is inside there appears to be circling, but that could also be an artifact, because we don't know that with this normal camera. On the other hand, in the beakers, you also see nice schlieren, which are caused by different temperatures, which is exactly what this method is supposed to do. It shows you changes in refractive index, here changes in density caused by temperature changes. If we now pull the beakers apart here, you will see that these shadows, which this talk is about mostly, stay, and they're extremely fast. So the only way actually to find out what's going on is to change from a normal camera, HD TV camera, to a high-speed visualization. And if you do that, you see much more. You see that they are ring-like structures. They're originating from the right side, which is the anode side. They're going to the left side. They're to some part reflected at the left side. They come with a certain frequency, and they have a certain velocity. Now, we have tried different configurations. They always move from anode to cathode. And yeah, in addition to the rings, what we see here are focal caustic and the surface reflections on the bridge. But let us focus on these shadow rings. Why do we see them? What is causing them? Well, they are produced by changes in the refractive index. This is what the method actually does. And such changes can be caused by density gradients due to temperature, or by local changes in polarizability of the molecules or molecular clusters. Now, we have seen in the beakers that there were changes due to temperature. It would be reasonable to assume that in the bridge the same thing is happening. So let's take a look at the bridge with a high-speed thermographic camera. Now, if we do that, many of you have seen this video before, we see that, yes, there are patterns and the temperature distribution is not uniform, but they look completely different from the shadow rings. So, yes, there is a temperature distribution, but it's not causing the shadow rings. Which means that, yeah, if it's not density gradients due to temperature, it could be local changes in polarizability. Well, in order to test that as an experimental physicist, let's do another experiment to verify that hypothesis. Well, if that is true, then these molecular clusters or entities, whatever they are, they should scatter laser light when illuminated from the side, because they would cause Rayleigh scatter. And if we do this experiment, you see that the laser light, as it enters the bridge, is actually visible, which means that it is scattered in this outer layer. And additionally, in this video, you see these tiny droplets above and below the bridge. These are just water droplets that are ejected from the surface of both beakers, because the surfaces are charged, electrospray events, and they are moving along the electric field lines. But the most important point here is we see the laser light, so this is another corroboration of our hypothesis that we're actually having something here in the outer layer that changes the refractive index, and it's not a temperature change. Now, let us further analyze the rings. What's their velocity and what's their frequency? Well, that can be easily done. You take a line, you integrate over time. You know that this distance in pixel is 9.68 millimeters. We calibrated it, you know, because of the frame rate, that 300 frame numbers is 0.03 seconds. So we get a velocity of 32 centimeters per second, plus minus a couple of centimeters, sometimes higher, sometimes a little bit lower. So we have something that moves through the bridge with 32 centimeters per second from anode to the cathode, never the other way around. What could it be? Well, we have found out earlier that protons move from the anode to the cathode through the bridge. And they always move from anode to cathode because they are produced at the anode due to electrolysis. They are more mobile than the hydroxyl ions, so there are no hydroxyl ions in the bridge. The recombination is somewhere in the catholyte, so yeah. But protons are protons and not rings. Why would there be any correlation, or why would the rings show the proton movement? Well, let's assume that they do, and let's make a hypothesis. First of all, if the shadow rings do visualize the protons, is the velocity the same as the ring velocity? Second, why is there a frequency? Because we are applying a DC current, so there should be a smooth current of protons, yet we see a frequency. So what's the frequency and how does it relate to protons? And finally, most importantly perhaps, how can microscopic objects as protons induce a macroscopic observable effect? Well, hypothesis one, what's the velocity in the bridge? Well, with quasi-elastic neutron scattering, we have shown that the proton mobility in the bridge is about twice as high as in the bulk. Now, when we have the proton mobility, the only thing that we need to calculate the proton velocity is the electric field strength. There have been a lot of simulations of this strength. We have recently also measured it, more or less corroborating these simulations. You see that across a 16 kilovolt bridge, the drop of potential is almost from 16,000 to 0. So really the bridge is the resistor in the system. The whole potential drop takes place across the bridge. And you can easily calculate, you get a field strength of about 5,300 volts per centimeter. Now, depending on which mobility you use, that we found for the water bridge or the classical one, you get two velocities, 50 centimeters per second for the water bridge and 25 for the bulk. But the shadow rings move at 32. I'm happy with that. So for me, this is faster than in normal water and same order of magnitude. It's not a perfect match, but the chance data was also not a perfect measurement. So for me, this is for the moment good enough to say, yes, the protons could be visualized as shadow rings, at least concerning their velocity. Now, hypothesis two, what is the ring frequency and how does it relate to the protons? Well, if we do a numerical simulation, which a colleague of mine, Professor Brizhik from TU Delft and his student Gautam are doing at the moment, they have very nice results and they can nicely simulate the flow in the bridge, and they show that at the bridge bases we have shear layers. So we have protonated water coming from one side into the bridge and normal water, bridge water, leaving the bridge, and these flows are right next to each other. Now, fluid dynamics tells us that shear layers always create vortices, as is nicely shown in this picture from Wikipedia here. And they move with the mathematics behind that is very simple. The velocity mu bar is just capital lambda times f. If we just make a ballpark figure calculation, we say it's about 1 millimeter, velocity is about 10 centimeters per second. We get the frequency of about 100 hertz plus minus 50. Well, so proton-enriched water from the analyte would enter the bridge with a 100 hertz oscillation. And if you take another look at the shadowgraphy and zoom in here at the bridge base on the right side, we can actually see that the oscillations take place here. We actually see, if we know what to look for, that there are two currents of water flowing next to each other. There's a shear layer, and actually the frequency is around 100-120 hertz. So although we have a constant proton production because of electrohydrodynamics, because of fluid dynamics, we get vortices and a variation of about 100 hertz. So that is also, for me, good enough to say, okay, we understand if these are protons, then we understand why they are pushed into the bridge with a frequency and not continuously. And now the most difficult part. How can microscopic objects induce a macroscopic effect? Well, let us a little bit remember how this whole investigation started. In the beginning, I thought, well, because the bridge doesn't fall down, there must be a different structure. However, theoreticians told us there can't be. The external field strength is 1,000 times too low to change the average structure of the bridge. We have ourselves confirmed that. In the meantime, other groups confirmed that the structure is the same. But then I ask you, is the structure a right tool to define and analyze a liquid? I would say no. Because a liquid is dynamic, and the dynamics in the water, they do change in the bridge at the molecular level. We have shown that the OH vibrational relaxation time is faster in the bridge than in the bulk and slower than in ice, meaning that the H bonds are much stronger. The thermalization dynamics showed that they are slower in the bridge than in bulk. This is some kind of a contradiction because it tells us that from one molecule to the next, the energy is passed very rapidly, but throughout the system it's not. So it seems as if there are regions with more strongly bound water molecules that are with borders where this bonding stops. And we have seen, as I have shown you before, that the proton mobility is enhanced. Well, if you have stronger H bonds, and you know that in ice you have actually proton bands, you can imagine that in the water bridge you have the onset of proton bands, which we call proton channels. And when they are forming, you should see an increased infrared emission in the water bridge compared to bulk water, which we also reported and published. So far, so good. What we now need is a theory that describes all of these changes without the need of having an additional structure. A theory that describes the interaction of a strong electric field that is applied with all the molecules involved and with their movement. And of course, Professor Giuseppe Vitiello, who is here with us, and the late Professor Del Giudice, provided us with this theory. And where the theory itself is mathematically very, very complicated, what it does is very, very logical. This field is not strong enough to change the average orientation of the molecules. But if you imagine that I'm a water molecule and the electric field now, you're the high voltage here, so electric field lines go through me. If I vibrate this way or perpendicular to the field line, that will make a big difference, even if the field is not strong enough to change my orientation. Which means that the symmetry of molecular oscillations is changed, it's broken. And in addition to that, the field allows the coupling of the vibrations which are alongside the field line. That is called Nambu-Goldstone coupling. So in a very simple diagram, if we increase the electric field strength, suddenly the symmetry changes. We have a new ground state, we have a completely new system. And at this certain field strength, a collective phonon coupling takes place, and the system enters a new state. And that new state is that provides us with the increased H-bond strength, the increased proton mobility, and so forth, without having to change the average structure. If that is true, this phonon coupling should be visible directly in the Raman spectrum. Actually, in 2016, there was a paper in Nature Communications by Elton and Fernandez Serra, and they said that the hydrogen bond network of water, just normal water, not a bridge, supports the propagation of optical phonon-like modes, of collective phonon modes. And they calculated that the lowest frequency vibrational Raman peak is actually a transverse optical phonon-like mode. So there is a phonon mode in water that does couple, that does allow phonon coupling. However, in normal water, according to their calculations, the propagation is only 0.3 nanometers for the transverse mode. If we have a macroscopic coupling of that mode in the water bridge, we should see that band in the Raman spectrum. Now, we did Raman measurements on the bridge, but that is complicated because of the geometry, because of the protons who are in there, because of the ever-changing diameter. So my friend and colleague Adam Wexler came up with a much more simple experiment. He just had a cuvette, a needle, a plate, where he applied a strong electric field to the water with a very, very simple geometry, where there's no electrolysis, no proton flow, just the field. And when we look at the Raman spectrum of that water at the same temperature and we compare 0 kilovolt to 20 kilovolt, we see an enhancement at about 420 wave numbers. Now, 420 wave numbers is not 435, but this is measurement. The other is a calculation. So again, for me, this is good enough. I say the vibration mode is enhanced by the applied field, and because the laser diameter is 0.1 millimeter, this coupling must extend at least 0.1 millimeters. Otherwise, if it was fluctuating, if it was smaller, these enhancements would cancel each other out. So we have phonon coupling that is actually macroscopic, and we think we have the same phonon coupling in the bridge. Now, phonons are actually sound waves, move with the speed of sound, so 1,526 meters per second, whereas the protons, as I've showed you, move with 0.32 meters per second, so they're much, much slower. In order to understand what's happening in the water bridge, it's like considering the protons as being standing still and the phonons moving past them. And because protons have a very strong electric field, so when the phonons were coupled and encounter them, they are distorted like waves breaking a rock. So in an analogy, we have here the water waves that come towards the shore, and if you think the rock bottom is our electric field, at some point here we have wave breaking, and that is actually the change of the refractive index, which we see in the bridge as ring. So the macroscopic system of coupled phonons is distorted in its whole by the protons, and that distortion becomes visible, and this is why we see a macroscopic effect creating a shadow ring. Now, Adam was so nice to find this picture of the beach of Nazaré in Portugal, where you have actually a real ocean floor gradient and nice waves coming in, and as you can see, this creates beautiful wave breaking close to the shore. So to summarize, our hypothesis was shadow rings visualize the proton movement through the bridge. Is the proton velocity the same? Yes, it's close to the predicted proton velocity using the quasi-elastic neutron scattering results. What is the ring frequency and how does it relate to the protons? It's around 100 Hertz caused by electrohydrodynamic shear flow and vortices, and the protons are entering that bridge with a higher and lower concentration at that frequency. And finally, how can microscopic objects, protons, induce a macroscopic observable effect? Well, thanks to a fruitful cooperation with Professor Giuseppe Vitiello, we think we can describe this with the help of quantum field theory, showing that there's phonon coupling, which we measure directly, and that is over macroscopic distances. It's only in one dimension, it's only the phonons that couple, nothing else, but that is good enough. And the influence of this microscopic disturbances like protons is translated through the coupling, thereby creating macroscopic phenomena. So I think the water bridge represents a state of water wherein quantum effects like vibrational coupling, proton band formation, and symmetry break have consequences concerning macroscopic properties. I'm not saying that water is a pure quantum fluid. If it was like that, it was simple. If water was helium-3, there wouldn't be any discussion about it. I would say that depending on the experiments you do and the questions you ask, you can reveal some quantum properties in water and, of course, also very classical fluid dynamic properties. Now, at this point, I'd like to say that none of this would have been possible without the help and support of Jacob Wojciechleger, my mentor and friend at the Graz Technical University. Adam Wexler, who did his PhD on the floating water bridge. My colleague and friend René Petschnik from TU Delft, who is now busy with really fully simulating this phenomenon, and his student, and very, very many other researchers throughout the world, many of them here in this audience who have helped me and supported me throughout years, making this all possible. And finally, of course, I thank you all very much for your attention.
Thank you so much, Elmar. Very inspiring. Okay, I think we're all wanting to go for the coffee break, but one or two questions maybe. Yes, Case, come over there.
Case.
Thank you, Elmar. It's always inspiring speaking, although I heard the story many times already. I still have a question. It's plain water. It's in you have 16, 20 kilovolts. Would you say this has any implications for biology or the interaction between cells and water, these findings?
Yeah, as we heard before from Professor Pokorny, there is evidence that similar electrical, I would say, conditions exist between the inside and the outside of living cells. So it is feasible to say that the water inside of the cell membrane could be in a similar state as the water in the water bridge. So normally when people ask me that, I always tell them, well, the water bridge, you consider water bridge some sort of a magnification of cellular water. So that in theory, when you do experiments with the water bridge, you also learn about cellular water. Whether this is true or not, I don't know, but I think it's a fair assumption.
Thank you so much for the wonderful presentation. I'm here.
Okay, hello.
Maybe you've talked about it before, but I've noticed one thing, that in the videos with the water bridge building, at first the water level is the same in both beakers. But as the bridge grows, the level in one of the beakers decreases, and it looks like the bridge is being built only from one of the beakers. So is it true, and why is it so?
There's always a slight surplus in the cathode beaker. So it is always going more water from the anode to the cathode beaker. In all cases, very seldom, not in all cases, let's say 90%, sometimes it's the other way around. We think it has to do with the proton flow, because this is also asymmetric. The protons are going, because they're faster, going through the water, through the bridge, and we think that it's like a diffusiophoresis. If you have a lot of protons, they drag water molecules with them, and this is changing and distorting the equilibrium. But if you put two balances below the beakers, you can see that it's actually always going up and down, and sometimes you have even an inverse situation.
Okay, good. Thank you, Elmar. I think that was the last question. Thank you again. And that was the end of this session, so now we have a coffee break. And please come back in 20 minutes, that's 25 past, and we will have poster cap.